This video is about making statistical inference about two means, mu sub 1 and mu sub 2. Recall that in making statistical inference about the single mean, we have a null hypothesis which implies that the true value of the parameter, which is mu, is equal to our guess or our hypothesized value. And on the other hand, we have an alternative hypothesis which implies that the true value of mu may be less than, greater than, or not equal to our guess or our hypothesized value. And whenever we make use of the less than or greater than in the alternative hypothesis, we are performing a one-tailed test. On the other hand, if we have not equal sign in the alternative hypothesis, we are performing a two-tailed test. Now, in making statistical inference about two means, we have two hypothesized means, mu sub 1 and mu sub 2. But unlike in making statistical inference involving a single mean, wherein we're trying to guess the true value of the parameter mu, in making statistical inference about two means, we're not actually after the true value of mu sub 1 and mu sub 2. But we're after the difference of mu sub 1 and mu sub 2. And if the difference between mu sub 1 and mu sub 2 is equal to 0, that is our null hypothesis, which implies that mu sub 1 is equal to mu sub 2. On the other hand, if mu sub 1 minus mu sub 2 is greater than 0, or in other words, mu sub 1 is greater than mu sub 2, that is one of the possible alternative hypotheses in performing a one-tailed test. The other possible alternative hypothesis is that if mu sub 1 minus mu sub 2 is less than 0, or in other words, mu sub 1 is less than mu sub 2. And lastly, of course, another possible alternative hypothesis is that when mu sub 1 minus mu sub 2 is not equal to 0, or in other words, mu sub 1 is not equal to mu sub 2, that is when we are performing a two-tailed test. Now, I'm going to show you some scenarios involving statistical inference involving two means. Let's say there are 8 patients, in which 4 patients receive treatment A and the other 4 patients receive treatment B. And suppose we're interested in the effect of those treatments in the platelet counts, in which platelet counts are only measured after given those treatments, then we may summarize the effect in the platelet count of treatment A using these 4 samples. And we may summarize it using X bar sub A. And similarly, we may summarize the effect of treatment B using the 4 samples, and let's denote it as X bar sub B. And by using these patients who receive treatment A or treatment B, we're making inference about the effect in the platelet counts of all the patients who receive treatment A or treatment B. Are they equal? That is our null hypothesis. Or maybe that the mean platelet count of all the patients who receive treatment A is greater than the mean platelet counts of all the patients who receive treatment B. That is our alternative hypothesis. And of course, another possible alternative hypothesis is that it is less than or not equal. Further, the mean platelet counts of all the patients who receive treatment A and the mean platelet counts of all the patients who receive treatment B, which are estimated using the 4 patients who received treatment A and B, notice that these means came from 2 separate groups. And when the 2 means came from 2 different groups, we say that the 2 means are independent. Thus, we may say that we are working with 2 independent means when we are working with 2 separate groups. Or in other words, when we have 2 groups in which they are just measured once, then we are working with 2 independent means. Note that assuming that these patients are assigned to which treatment at random, then this test for 2 means is applicable in randomized controlled trials wherein you have 2 groups, let's say a placebo group and a treatment group. And of course, this test may also be applied in analytical cross-sectional studies wherein it simply compares 2 groups. Now, let's say still you have 8 patients, but this time you're not interested in the effect of the 2 treatments. This time, let's say you're interested in the comparison before and after the treatment. So in this case, you have the platelet counts before or baseline, and let's say 7 days after the treatment. So in that case, you may compute for the mean platelet count before and the mean platelet count 7 days after the treatment. And suppose what you're interested in is the mean platelet counts of all the patients before and let's say 7 days after the treatment. Are they equal, implying that the treatment has no effect? That is our null hypothesis. Or maybe that the mean platelet count before is less than the mean platelet count after given the treatment, which implies that the treatment is effective in increasing the platelet count. That is one of the possible alternative hypotheses. Now note that these two means did not come from two separate groups because as you can see, they come from a single group. And when two means come from a single group, we call those two means as dependent. So note that if a study involves a single group given a single treatment but measured twice, then you are working with two dependent means. Thus, a statistical inference involving two dependent means may be applied in self-controlled trials, and even in what we call the matched pairs design. To illustrate what matched pairs design is, suppose still you have 8 patients given treatments A and B, but this time they are matched. Matched in terms of, let's say, age, sex, and BMI. As we can see here, the first patient who was given treatment A is an 18-year-old male with normal BMI. And matching that is the first patient who received treatment B, who happens also to be 18-year-old male with normal BMI. Similarly, the second patient who received treatment A, who is a 30-year-old female who is overweight, matches the second patient who was given treatment B, who is also 30-year-old female who is overweight. Likewise, the third patient who received treatment A is a 42-year-old male who is underweight. And matching that is the third patient who received treatment B, who happens also to be 42-year-old male who is underweight. And lastly, the fourth patient who was given treatment A, who happens to be 50-year-old female with normal BMI, matches with the fourth patient given treatment B, who also happens to be a 50-year-old female with normal BMI. Now, since patient numbers 1 and 5 are matched, numbers 2 and 6 are matched, 3 and 7 are matched, and numbers 4 and 8 are matched, we may consider this means as dependent, in which each pair of observations are patients with some matched characteristics. Thus, we may analyze this data given the sample mean of A and the sample mean of B, and suppose we want to make statistical inference in the effect of treatment A and B in the platelet counts of all the patients. Are they equal? That is our null hypothesis. Or are they not? Suppose that is our alternative hypothesis. And again, since these two values of mu, although came from two separate groups, but since they are matched, then we may consider them as dependent. Just note that if there are no information about the patients are given, then there's no way for us to identify whether they are matched or not, unless of course it is stated. So note that, again, two dependent means are not only for single group measured twice, but also when pairs are matched. Now, in making statistical inference about two independent means, we have three tests to consider. We have the student's t-test, the Welch t-test, and the z-test for two means. But z-test for two means is only applicable when the population variances sigma squared sub 1 and sigma squared sub 2 are known. Thus, if the population variances sigma squared sub 1 and sigma squared sub 2 are unknown, we shall make use of either the student's t-test or the Welch t-test. Student's t-test is used when the population variances sigma squared sub 1 and sigma squared sub 2 are assumed to be equal, while the Welch t-test is used when the population variances sigma squared sub 1 and sigma squared sub 2 are evidently unequal. And note that the student's t-test and the Welch t-test are collectively known as the two sample t-tests or simply the independent t-tests. And just so you know, the student's t-test is named after William Seeley Gossett under the pseudonym Student. He is an English statistician who also developed the t-distribution. And on the other hand, the Welch t-test is named after an English mathematician, Bernard Lewis Welch. Now, further to determine whether the population variances sigma squared sub 1 and sigma squared sub 2 may be assumed to be equal or not, we have to make use of a separate test, which is what we call as the F-test for two variances, in which I'll show you in the succeeding examples. In the meantime, just to determine whether you're going to make use of the student or the Welch t-test, we may consider what we call again as the f-test for two variances. Before we proceed with examples, let me show you some assumptions involving the test for two independent means. Here we see two normal distributions with means mu sub 1 and mu sub 2. And as you observe, they have the same variability. Thus, this is the case when we may assume that the population variances sigma squared sub 1 and sigma squared sub 2 are equal. On the other hand, on the next figure, still we can see two normal distributions with means mu sub 1 and mu sub 2. However, they differ already in the variability. Thus, this is the case when the population variances sigma squared sub 1 and sigma squared sub 2 are not equal. As for the test for dependent means, we just have a single formula which is in this form. Now let's proceed to example number 1.
A study wanted to determine if the number of times employees visit a doctor per year differ according to the health insurance program, Medicare versus regular. Data are shown below. Assuming equal population variances, do this data provide sufficient evidence that the mean number of visits to a doctor of all employees with Medicare differ with the mean number of visits to a doctor of all employees with regular insurance program? Test at 5% level of significance.
It is clear here that we have two groups of employees. One group under the Medicare insurance program and another group under the regular insurance program. Thus, it is clear that we are working with independent means. And since it is asking if the mean number of visits to a doctor of all employees under the Medicare insurance program differ with the mean number of visits to a doctor of all employees under the regular insurance program, then our null hypothesis is that the mean number of visits to a doctor of all the employees in the Medicare insurance program is equal to the mean number of visits to a doctor of all the employees in the regular insurance program. And of course, our alternative hypothesis is the mean number of visits to a doctor of all the employees under the Medicare insurance program is not equal or differ with the mean number of visits to a doctor of those under the regular insurance program. Now, to determine whether we're going to conclude in favor of the null or the alternative hypothesis, of course, we're going to compute for the test statistic. And since this involves two independent means, then we're going to make use of either the student's t-test, the Welch t-test, or the z-test for two means. However, it's obvious that the population variances are not known, so we're not going to make use of the z-test for two means. So it's only a matter of choosing between the student's or the Welch t-test. And since it's stated that assuming population variances, then it's clear that we're going to make use of the student's t-test. Given the two groups, Medicare and regular, you may assign which is group 1 and group 2. Now, suppose you choose Medicare as your group 1 and regular as group 2, then it follows that the mean number of visits of those in the Medicare, which is 4.0, is your x bar sub 1. And the mean number of visits of those in the regular program, which is 1.50, is your x bar sub 2. And it follows that the sample variance for those in the Medicare program is your s squared sub 1, and on those in the regular program is your s squared sub 2. And it follows as well that the sample size n of those in the Medicare is your n sub 1 and those in the regular program as your n sub 2. Then all we have to do is to substitute those values in the formula. So x bar sub 1 is 4.0, x bar sub 2 is 1.50, s squared sub 1 is 4.667, s squared sub 2 is 1.90, n sub 1 is 7, and n sub 2 as 6. Now, as for this part of the formula wherein we have mu sub 1 minus mu sub 2, although we do not have the actual values of mu sub 1 and mu sub 2, however, in the null hypothesis, it is stated that the two population means are equal. Thus, mu sub 1 minus mu sub 2, if these two means are equal, then the difference of this is 0. And substituting those values in the equation, we're going to have t as equal to 2.4337. And as for the df, which is n sub 1 plus n sub 2 minus 2, since n sub 1 is 7, n sub 2 is 6, then we're going to have df which is equal to 11. And to determine whether that test statistic is in the area of rejection or not, we have to compare it to a critical value. And the critical values may be found using the table of critical values for t-test. And since this is not equal sign, which indicates that we are performing a two-tailed test with DF of 11 at 5% level of significance, taking a look at the table under the two-tailed column 0.05 with DF of 11, we're going to have a critical value which is 2.2010, which in R may also be generated using QT 0.025 and then the degrees of freedom which is 11. Then the other one is QT, then 0.975, comma, then the same degrees of freedom which is 11. So we're going to have positive 2.2010 and negative 2.2010, which indicates that if we have this t distribution in which the blue lines represent the critical values which are negative 2.2010 and positive 2.2010, in which its areas to the extreme represented by the pink region are both 0.025, which when added together, we're going to have 0.05, which is the level of significance. Now, since these are the areas of rejection, the question is, where is 2.4337? Is it in the area of rejection? Yes, it is. Thus, since it's in the area of rejection, then we're going to reject the null hypothesis and conclude that there is sufficient evidence that, state the alternative hypothesis, the mean number of visits to a doctor of all employees with Medicare is not equal to the mean number of visits to a doctor of all employees with regular insurance program. And as for the p-value, we may compute that by getting the area to the extreme of t equals 2.4337 as well as the area to the extreme of t equals negative 2.4337 since this is a two-tailed test. And in R, we may generate that by using 1 minus pt, parenthesis 2.4337, comma, and then the degrees of freedom, which is 11. And the other one is just pt, parenthesis, negative 2.4337, comma, 11. Or you may just simply get one of those and multiply it to 2. And we're going to have a p-value, which is 0.0332. Which indicates that the probability that the observed value in which the difference is not 0 happened by chance is just 3.32%. And comparing it to 5%, that is relatively small. Thus, there is no reason to doubt the alternative hypothesis. That is why our conclusion is in favor of the alternative hypothesis. And further, we may write the result as there is sufficient evidence that the mean number of visits to a doctor of all employees with Medicare is not equal to the mean number of visits to a doctor of all employees with regular insurance program. Then simply write the p-value.
To measure the effectiveness of a drug for asthmatic relief, 12 patients all susceptible to asthma were each randomly administered either the drug or a placebo during 2 separate asthma attacks. After 1 hour, an asthmatic index was obtained on each subject with the following results. Do the data provide sufficient evidence that the mean asthmatic index of all patients treated with the drug is less than those treated with placebo? Test at 5% level of significance.
It is clear here that we are working with 2 separate groups, thus this involves 2 independent means. And since it is asking if there is sufficient evidence that the mean asthmatic index of all patients treated with the drug is less than the mean asthmatic index of those treated with the placebo, then our null hypothesis is that the mean asthmatic index of all patients treated with the drug is equal to the mean asthmatic index of all the patients treated with the placebo. And our alternative hypothesis is that the mean asthmatic index of all the patients treated with the drug is less than the mean asthmatic index of all the patients treated with the placebo. And again, to determine whether we're going to conclude in favor of the null or the alternative hypothesis, we have to compute for the test statistic. And since this involves 2 independent means, we have to choose whether we're going to make use of the student's t-test, the Welch t-test, or the z-test for 2 means. However, it is clear that the population variances are still unknown, thus we're not going to make use of the z-test for two means. So we are left with two choices, which are the student's t-test and the Welch t-test. However, there's no statement implying whether the population variances may be assumed to be equal or not. Thus, we have to make use of a separate test this time, which is the f-test for two variances. In the f-test for two variances, we have a null hypothesis which implies that the population variances are equal. And we have an alternative hypothesis in which the population variances are not equal. Thus, as you can see, if our conclusion will be in favor of the null hypothesis, then that implies that we're going to make use eventually of the student's t-test, because the student's t-test assumes equal population variances. And on the other hand, if our conclusion will be in favor of the alternative hypothesis, then that implies that we're going to make use eventually of the Welch t-test, because the Welch t-test assumes unequal population variances. And as for the F statistic, we're going to make use of this equation in which, since F has 2 degrees of freedom, df1 will be computed as n sub 1 minus 1 and df2 is computed as n sub 2 minus 1. So applying the f-test for two variances in example number 2, our null hypothesis is that the population variances are equal, or in other words, the variance asthmatic index of all patients treated with the drug is equal to the variance asthmatic index of all patients treated with the placebo. And our alternative hypothesis is that the population variances are not equal, indicating that the variance asthmatic index of all patients treated with the drug is not equal to the variance asthmatic index of all patients treated with placebo. And computing for the test statistic F, applying this equation, we may choose which one will be group 1 and which one will be group 2. Assuming that the patients treated with the drug is group 1 and those treated with the placebo as group 2, then these standard deviations will be your S sub 1 and S sub 2. And using those values to compute for the test statistic F, then S sub 1 here will be 8.1833 and S sub 2 here will be 3.9370. And note that since these are standard deviations, we have to square that to get the F statistic, since F statistic is the ratio of two variances. Now, regarding sigma squared sub 1 and sigma squared sub 2, since under the null hypothesis, it's stated that the population variances are equal, then although we do not have the actual values of sigma squared sub 1 and sigma squared sub 2, since they are assumed to be equal, then these two denominators in the F statistic will just be simply cancelled out, leaving us with S squared sub 1 over S squared sub 2. And again, substituting S sub 1 as 8.1833, then square, divided by 3.9370, then square, we're going to have a value of F of 4.3204. And since 8.1833 came from 6 samples and 3.9370 came from 6 samples as well, then your DF1 is 6 minus 1 and your DF2 is also 6 minus 1. So we're going to have a DF1 and DF2 of both equal to 5. And again, that is the case when you consider those patients treated with the drug as group 1 and those patients treated with the placebo as group 2. Now, another possible case is when those patients treated with the placebo is considered as group 1 and those patients treated with the drug as group 2. And if that is the case, then this will be your S sub 1 and this will be your S sub 2. And it follows that this is your N sub 1 and this is your N sub 2. And substituting S sub 1 as 3.9370 and S sub 2 as 8.1833. And again, sigma squared sub 1 and sigma squared sub 2 will just be cancelled out since under the null hypothesis they are assumed to be equal. Then another possible value of F is 0.2315. in which the df1 is 6 minus 1 and df2 is 6 minus 1, which are both equal to 5. And to determine whether that f statistic is in the area of rejection, we have to find the critical values. Now, the f distribution looks like this. And what you must notice is that the leftmost part of the f distribution is 0, which indicates that the f statistic can never be equal to a negative value. Since the f statistic is simply the ratio of two sample variances, regardless of the population variances, since the population variances will just be cancelled out under the null hypothesis that they are equal. Since the sample variance 1 and sample variance 2 can never be negative since they are variances, then the f statistic can never be a negative value. Thus, f statistic is always a non-negative value. Now, unlike the z and the t distribution, in which the one on the center is t is equal to 0 or z is equal to 0, which implies that the null hypothesis is true, or in other words, let's say mean sub 1 or mean sub 2 is equal to 0. Now, the f statistic, our reference is not 0, but 1. Which implies that when f is equal to 1, then that supports the null hypothesis in which the population variances are equal. Because when the population variances are equal, the ratio is equal to 1. And the one on the right side of f is equal to 1, or in other words, when f is greater than 1, that implies that the ratio of the two variances is greater than 1. Or in other words, the variance of the numerator is greater than the denominator. And on the contrary, when f is less than 1, that implies that the ratio of the two variances is less than 1, indicating that the one in the numerator is less than the one in the denominator. So similarly, to find the critical values of f, we have to consider two regions in which the area to the extremes are both equal to 0.025, just like the z and the t distribution. So that when added together, 0.025 and another 0.025 will have 0.05, which is our level of significance. And we may generate that in R using Q, then F, then 0.025, and then the 2 degrees of freedom, which is again our n sub 1 minus 1 and our n sub 2 minus 1. And the other one is QF, and then 0.975, and then the same degrees of freedom, df sub 1 and df sub 2. So using the table, we have two tables for the critical value of f. One for the left tail, in which the uppermost row indicates the df1, and the leftmost column is for df sub 2. Thus, if you have df1 of 5 and df2 which is 5, then our critical value on the left side is 0.140, which again may be generated using QF 0.25, 5, 5. On the other hand, finding the critical value on the right tail of the F distribution, again the uppermost row is for the df1 and the leftmost column is for the df2. And similarly, when your df1 is 5 and df2 is also 5, then the critical value for the right tail is 7.146. Which again may be generated in R using QF, then 0.975, 5. And again, illustrating that, suppose this is the F distribution, and we have our reference in which that is F is equal to 1, then our critical values on the left and on the right are F is equal to 0.140, and the other one is F is equal to 7.146. Indicating that this is 0.025 and this is also 0.025. Now the question is, where is 4.3204 or 0.2315? Is it in the area of rejection? No, it's not. Thus, we're not going to reject the null hypothesis and conclude that there is no sufficient evidence that the population variances are not equal. And since the population variances are not evidently unequal, then we're just going to assume that the population variances are equal, which indicates that we are going to make use of the student's t-test. Now for the p-value, since again the p-values are the area to the extreme, then we're just going to compute for the area of this region and the area of this region. And computing for this region, we're going to make use of PF, and then the F statistic 0.2315, and then its degrees of freedom, which are both equal to 5. And the other one, since this is on the right tail of the curve, this is 1 minus PF, then 4.3204, and then its degrees of freedom, which are both equal to 5. Then all we have to do is to add those two p-values. And we're going to get a p-value of 0.1342. And similarly, we may just get that p-value by just multiplying to 2 either this or this one. And we will still have the same p-value, which is 0.1342. And similarly, we're going to interpret the p-value in which 0.1342 indicates that the probability that the observed value in which the sample variances ratio is not equal to 1, or in other words, the sample variances are not equal, happen by chance is 13.42%, in which compared to 5% is relatively large. Thus, there is a reason to doubt the alternative hypothesis. That is why our claim is in favor of the null hypothesis. And since it was not evident that the population variances are unequal, then the population variances sigma squared sub 1 and sigma squared sub 2 may just be assumed to be equal. Thus, we're going to make use again of the student's t-test. And applying the student's t-test, the same formula that we had in example number 1, assuming that this is group 1 and assuming that this is group 2, then this is x bar sub 1, this is x bar sub 2, this is s sub 1, and this is s sub 2. And it follows this is n sub 1 and this is n sub 2. So n sub 1 here is 22.833. X bar sub 2 is 29.500. N sub 1 are all equal to 6. N sub 2 likewise are all equal to 6. Then as for S sub 1, we're going to make use of 8.1833 and S sub 2 as 3.9370. Note that we have to square those standard deviations since the one inside the square root here are variances. And lastly, as for the mu1 minus mu2, since the null hypothesis assumes equality, then this is assumed to be equal to 0. So substituting those values, we're going to have t, which is equal to negative 1.7982. And the degrees of freedom, which is n sub 1 plus n sub 2 minus 2, so that is 10. And again, we have to compare the test statistic t to a critical value, and we have to make use of the critical values for t-test. Now, since this is a less than sign indicating that this is a one-tailed test, at 5% level of significance with DF of 10, so one-tailed 0.05 DF of 10, our critical value is 1.8125. And again, the critical values sign depends on the test statistic for one-tailed test. Since this is negative, then our critical value is negative 1.8125, which we may also get using R by using QT and then 0.05, comma, the degrees of freedom, which is 10. Again, this is 0.05. It is because it is one-tailed and a negative test statistic. This should be 0.95 if this is one-tailed and a positive test statistic. So going back, we have negative 1.8125 as the critical value, indicating that the area to the extreme is 0.05, which sets this area as the area of rejection. Now the question is t equals negative 1.7982 in the area of rejection? Is actually not. Thus, we're not going to reject the null hypothesis and conclude that there is no sufficient evidence, then state the alternative hypothesis.
that the mean asthmatic index of all patients treated with the drug is less than those treated with placebo. For the p-value, we may just get the area to the extreme of this test statistic, so that is pt, and then negative 1.7982, comma, then the degrees of freedom, which is 10. And we're going to get 0.0511, indicating that the probability that the observed value, which is not equal to 0, happened by chance by 5.11%. And 5.11% relative to 5% is considered large. Thus, there is a reason to doubt the alternative hypothesis. And further, we may write the result as there is no sufficient evidence that the mean asthmatic index of all patients treated with the drug is less than those treated with placebo. And then the p-value, which is 0.051.
Moving on, let's have example number 3, which is a cross-sectional analytic study.
A group of researchers wanted to compare the mean platelet counts of patients diagnosed with dengue fever and those diagnosed with chikungunya fever. 27 patients of each group participated and results are as follows. At 5% level of significance, do the data provide sufficient evidence that the mean platelet count of all patients diagnosed with dengue fever differ with those diagnosed with chikungunya fever?
Since this involves two separate groups, then still we're working with two independent means. And since the problem is asking if the mean platelet counts of all the patients diagnosed with dengue fever differ with the mean platelet counts of all the patients diagnosed with chikungunya, then our null hypothesis is that the mean platelet counts of all the patients diagnosed with dengue fever is equal to the mean platelet counts of all the patients diagnosed with chikungunya. And our alternative hypothesis is that the mean platelet counts of all the patients diagnosed with dengue fever differ or is not equal with the mean platelet counts of all the patients diagnosed with chikungunya. And of course, again, to determine whether we're going to conclude in favor of the null or the alternative hypothesis, we have to compute for the test statistic. And since this involves two independent means, we have to choose again whether we're going to make use of the student's t-test, the Welch t-test, and the z-test for two means. However, there are no actual values of the population variances, so again, we're not going to make use of the z-test for two means. So we are left with two choices, the student's t-test and the Welch t-test. And since it is not stated whether the population variances is assumed to be equal or not, then we have to perform again the f-test for two variances.
Applying the f-test for two variances in example number 3, of course, the null hypothesis would still be that the population variances are equal, and the alternative hypothesis will be that the population variances are unequal, in which this implies that if our conclusion will be in favor of the null hypothesis, we're going to make use of the student's t-test, and if our conclusion will be in favor of the alternative hypothesis, then we're going to make use of the Welch t-test. So for the null hypothesis, that implies that the variance of the platelet count of all patients diagnosed with dengue and chikungunya fever are equal. And the alternative hypothesis is that the variance of the platelet count of all patients diagnosed with dengue and chikungunya are not equal. And computing for the test statistic F, suppose this is our group 1 and suppose this is our group 2, then substituting 76.9148 as the value of S sub 1 and substituting 16.0489 as the value of S sub 2. And again, we have to cancel out sigma squared sub 1 and sigma squared sub 2 because under the null hypothesis, they are equal. Thus, our computed value of F is 22.968. And as for the degrees of freedom, since there are 27 patients of each group, indicating that n sub 1 is 27 and n sub 2 is also 27, then our degrees of freedom are both equal to 26. And again, this is the case when we considered those with chikungunya as group 1 and those with dengue fever as group 2. Now, if it's the other way around, wherein those with dengue are considered as group 1 and those with chikungunya are considered as group 2, then substituting 16.0489 as your S sub 1 and 76.9148 as your S sub 2, we're going to have a value of F which is 0.044. And again, since both groups have 27 patients, then our DF1 and DF2 are both equal to 26. And when asked when these F statistics are in the area of rejection, we have to consider the critical values. And for the critical values, since our table is limited to some degrees of freedom, in which as you can see there is no DF1 of 26 as well as DF2, then we just have to make use of R to generate the critical values. So we're going to make use of QF and then 0.025 and then the 2 degrees of freedom, DF1 which is 26 and DF2 which is also 26. And as for the right tail, similarly, our table is limited to some degrees of freedom. So DF1 of 26 and DF2 of 26 cannot be seen on the table. So we're just going to make use of R to generate the critical values. So that is QF 0.975 and then the DF1 and DF2 which are both equal to 26. And illustrating it, suppose this is our F distribution in which our reference is when F is equal to 1. Thus, the left critical value is when F is 0.456 and the other one is when F is equal to 2.194, indicating that the area on both sides of the extreme are both 0.025, which of course when summed up is our level of significance, which is 0.05. Now the question is 22.968 and 0.044 in the area of rejection? Yes, it is. So our decision will be to reject the null hypothesis and conclude that there is sufficient evidence that the population variances are not equal, indicating that we're going to make use of this time the Welch t-test. And as for the p-value, we just have to calculate the area to the extreme of those test statistics, in which this one is PF 0.044, 26, 26, and this one, since it's on the right tail, is 1 minus PF of 22.968, 26, 26. And just add them together to generate the p-value, in which we're going to get a very small p-value that is less than 0.001. So again, if the p-value is extremely small, we just have to write it as less than 0.001. And of course, similarly, we may compute that p-value by getting any of this and then just multiply it to 2. Anyway, again, the p-value of less than 0.001 implies that the probability that the observed value in which the ratio of the two variances, which is not equal to 1, happen by chance is less than 0.1%, which is extremely small. Thus, there is no reason to doubt the alternative hypothesis. That is why our conclusion this time is in favor of the alternative hypothesis, which implies that we're going to make use of the Welch t-test.
Now, since the population variances this time is evidently unequal based on the F-test for two variances, then we're going to make use of the Welch t-test.
So we just have to substitute x bar sub 1, x bar sub 2, s sub 1, s sub 2, n sub 1, and n sub 2. So suppose this is our group 1, so this is our x bar sub 1, and suppose this is our group 2, then this is our x bar sub 2. And it follows that this is S1 and S2. So x bar sub 1 will be 55.1852. X bar sub 2 is 271.7407. S sub 1 here is 16.0489. N sub 1 is 27. S sub 2 is 76.9148. Don't forget to square. And then N sub 2 is 27. And again, mu sub 1 minus mu sub 2 is not actually given, but under the null hypothesis is assumed to be equal, then this is assumed to be equal to 0. So substituting those values, we're going to have t which is equal to negative 14.321. And for the degrees of freedom, we just have to substitute the same values for S sub 1, S sub 2, N sub 1, and n sub 2. And we're going to have a DF which is equal to 28.260. And comparing that test statistic with the critical value, in which we may get using the table, using two-tailed since this is not equal sign, 5% level of significance, and DF which we will just approximate using 28 on the table. So this is two-tailed 0.05, approximately 28, so we're going to have 2.0484. And again, since this is a two-tailed test, we're going to make use of positive, negative 2.0484, which in R we may get using QT 0.025 and another one which is QT 0.975, and then the degrees of freedom 28.260, which we're going to get positive and negative 2.0476. Which implies that if this is the t-distribution, the blue line again is the critical value, in which the area to the extreme, which are both 0.025 when added, is the level of significance, which again sets the area of rejection. So the question is, where is t equals negative 14.321? Is it in the area of rejection? Yes, it is in the area of rejection. Thus, we're going to reject the null hypothesis and conclude that there is sufficient evidence that the mean platelet count of all patients diagnosed with dengue fever differ with those diagnosed with chikungunya fever. As for the p-value, we may just get the area to the extreme of both positive and negative 14.321. So we may get that using 1 minus PT and then 14.321 comma 28.260, and the other one which is PT negative 14.321 comma 28.260. Add these two values, or simply we just have to multiply any of them by 2. We're going to have a value which is very small when rounded off to 3 decimal places, that's 0. So we're going to write it as less than 0.001, which indicates that the probability that the observed value in which the difference is not 0 happened by chance by less than 0.1%. And relative to 5%, that is very small. Thus, there is no reason to doubt the alternative hypothesis. That's why we concluded in favor of the alternative hypothesis. And similarly, we may write the result as there is sufficient evidence that the mean platelet count of all patients diagnosed with dengue fever differ with those diagnosed with chikungunya fever. And then the p-value.
A study wanted to compare the parasite density in parasites times 10⁻³ per microliter of hospitalized children diagnosed with malaria with and without sickle cell disease or SCD. A total of 70 children were gathered, and results show that the mean parasite density of those with SCD is 67.77, while children without SCD is 95.32. Assuming that their population variances from normal distributions are 2,400 with SCD and 4,000 without SCD, is there sufficient evidence that the mean parasite density of all hospitalized children diagnosed with malaria but without SCD is higher than those with SCD? Test at 5% level of significance.
Now, this study compares the parasite density of all the children diagnosed with malaria. And those children diagnosed with malaria are divided into two groups. One group with sickle cell disease and another group without the sickle cell disease. Now, given the sample means together with the population variances, the problem is asking if there is sufficient evidence that the mean parasite density of all hospitalized children diagnosed with malaria but without sickle cell disease is higher than those with sickle cell disease. So our null hypothesis here is that the mean parasite density of all the hospitalized children diagnosed with malaria but without sickle cell disease is equal to the mean parasite density of all the hospitalized children but with sickle cell disease. And the alternative hypothesis is that the mean parasite density of all hospitalized children diagnosed with malaria but without sickle cell disease is higher than the mean parasite density of all hospitalized children with sickle cell disease. And again, to determine whether we're going to conclude in favor of the null or the alternative hypothesis, we have to compute for the test statistic. And since this deals with two independent means, we have to choose whether we're going to make use of the student t-test, the Welch t-test, or the z-test for two means. And apparently, the population variances here are given, which are 2,400 and 4,000. So this time, we're going to make use of the z-test for two means.
All we have to do is to substitute the values for x bar sub 1 and x bar sub 2, which are 67.77 and 95.32. For mu1 minus mu2, again, it's not given, but under the null hypothesis, it's assumed to be equal, so that is 0. For sigma squared sub 1, that is the variance of children with the sickle cell disease, so that is 2,400. And n sub 1 is the number of patients with sickle cell disease, so that is 33. And for sigma squared sub 2, that is the variance of patients without the sickle cell disease, so that is 4,000 divided by n sub 2, so that is the number of patients without the sickle cell disease, so that is 37. And substituting those values, we're going to have negative 2.049. Next, for the critical value, we simply have to make use of the critical values for z-test. And since this is one-tailed test at alpha 0.05, one-tailed test at alpha 0.05, we just simply have to choose whether 1.645 or negative 1.645. Since the computed value is negative, then we have to make use of negative 1.645. Or in R, we may make use of Q norm and then 0.05. So this indicates that the blue line is negative 1.6449 and the area to the extreme is 0.05. Now the question is, where is negative 2.049? Is it in the area of rejection? Is actually yes, it's in the area of rejection. That's why we're going to reject the null hypothesis and conclude that there is sufficient evidence that the mean parasite density of all hospitalized children diagnosed with malaria but without sickle cell disease is higher than those with sickle cell disease. And lastly, for the p-value, we may just have to compute for the area from this test statistic to the extreme. And that may be computed using p-norm of negative 2.049. And that gives us 0.02, which implies that the probability that the observed difference is not 0, this case is 27.55, happened by chance by just 2%. And relative to 5%, that is small, thus there's no reason to doubt the alternative hypothesis. Thus, our claim is in favor of the alternative hypothesis. So we may write the result as there is sufficient evidence that the mean parasite density of all hospitalized children diagnosed with malaria but without sickle cell disease is higher than those with sickle cell disease.
Before we proceed with the next example, let me share a statistical trivia about the f-test for two variances. Because what you may have noticed is that when df sub 1 and df sub 2 are infinitely large, or in other words, when the sample size of the two groups are very, very large, because as you know, df sub 1 is computed as n sub 1 minus 1, and df sub 2 is computed as n sub 2 minus 1, the critical value of f is equal to 1.00, which indicates that whatever f that you have computed, surely it will be in the area of the rejection. Unless, of course, your computed f is exactly 1.00, which is almost impossible. Thus, when the sample size of the two groups are very, very large, let's say thousands or probably millions, the null hypothesis will be rejected, which implies that the population variances are unequal. In other words, when the sample size of the two groups are very, very large, you may already use the Welch t-test. Because as you know, the Welch t-test is used when the population variances are evidently unequal. Consider that in most researches, using F-test prior to the use of any two-sample t-test, whether that's student's t-test or Welch t-test, is not advised. This is because what we call multiple hypothesis testing, which in our case we use F-test first, then eventually we use a student's or the Welch t-test, increases what we call the type 1 error or the alpha. Thus, in practice, unless there's a separate research that reports that the population variances are unequal, then that's the only time that the Welch t-test is applied. That is why in most researches, student's t-test is more frequently used as compared to the Welch t-test. Now moving on, let's have making statistical inference involving two means, and this time they are dependent. Note that again, this is used when you have a single group measured twice, or probably two groups but matched pairs. For the formula of the t-test for dependent means, or also known as the paired t-test, we have this equation wherein t is equal to x bar sub d minus mu sub d all over s sub d divided by the square root of n, in which this t distribution has n minus 1 degrees of freedom. Now in example number 5, this is about a group of researchers who wanted to determine whether there's an improvement or an increase in the mean CD4 count of all stage 4 HIV patients after taking antiretroviral therapy for 6 months. Take a look at this.
A group of researchers wanted to determine if there is an improvement in the CD4 count of stage 4 HIV patients 6 months monitoring phase after taking the antiretroviral therapy or ART. The results are shown below. Do the data provide sufficient evidence that the mean CD4 count of all stage 4 HIV patients increased 6 months after taking ART test at 5% level of significance?
So note that this time this is a single group in which their CD4 count were measured before and 6 months after taking the antiretroviral therapy. In other words, this is a single group measured twice. Thus, we're going to make use of the t-test for dependent means, also known as the paired t-test. And since the problem is asking if there's sufficient evidence that the mean CD4 counts increase 6 months after, as you can see on the data, there's additional column which is increase, which is simply the CD4 count after 6 months minus the baseline. So as you can see, 221 minus 41, we have 180. 171 minus 51, we have 120. And same thing follows with the other patients. And I computed here the sample mean, which is 121.22. So if the patient has increased CD4 count before and then after, it shows that in the increased column, the value is positive. And it follows that if the mean increase is positive, then that shows an improvement in the CD4 count. In other words, the x bar sub d here is the mean of the differences of the before and after. And the standard deviation of the differences is actually your s sub d. Now, for the null hypothesis here, if the CD4 count of patients did not change, then the increased column contains 0. Or in other words, the mean is 0. So our null hypothesis here implies that among patients taking the antiretroviral therapy, the mean difference or mu sub d is equal to 0, indicating that the antiretroviral therapy is not effective in increasing the CD4 count of the patients. And the alternative hypothesis here is that mu sub d is greater than 0, which implies that there's an improvement in the CD4 count of the patients, or in other words, the antiretroviral therapy is effective in increasing the CD4 count of all the stage 4 HIV patients 6 months after taking the therapy. So what this shows is that you have a sample mean which is 121.22 coming from 9 patients. If we collect the entire population or the entire patients who took the therapy, are we going to have a mean which is greater than 0? That is our alternative hypothesis. Or just equal to 0, which is our null hypothesis.
So substituting 121.22 as the value of x bar sub d, 58.49098 as the value of s sub d, and 9 as the value of n, this will be 121.22 S sub D will be 58.49098 and the value of N is 9. And although we do not have the value of mu sub D, but under the null hypothesis it is equal to 0, then mu sub D here will be equal to 0. Thus our value of T is 6.217 with degrees of freedom which is N minus 1, so this is 9 minus 1, and that gives us a degrees of freedom of 8. Now, finding the critical value, all we have to do is to make use of the table for critical values for t-tests. And since this is greater than, implying that we are performing a one-tailed test at alpha 0.05 with df of 8, then under one-tailed column, alpha 0.05 and df of 8, we're going to have a critical value of 1.8595. And since the calculated value of t is positive, and since this is one-tailed, then our critical value is t equals positive 1.8595, which we may also get using r using qt, and then 0.95, 8. Since if this is the t distribution, this is 0.05, thus this is 0.95. That's why we're making use of 0.95. Leaving us with this area of rejection. So the question is, where is 6.217? Is it in the area of rejection? Yes, it is. Thus, our decision is we're going to reject the null hypothesis and conclude that there is sufficient evidence that the mean CD4 count of all stage 4 HIV patients increased 6 months after taking the antiretroviral therapy. Then as for the p-value, we just have to get the area to the extreme of this test statistic, which is 1 minus pt, then the value of t, which is 6.217, and the degrees of freedom, which is 8, which we're going to get a very small p-value, which when rounded off to 3 decimal places is 0.000. Thus, we're just going to write it as less than 0.001. Which implies that the probability that the observed value in which the mean of the differences is not 0 happened by chance is less than 0.1%, which is extremely small as compared to 0.05. Thus, there is no reason to doubt the alternative hypothesis. That is why our conclusion is in favor of the alternative hypothesis.
Now let's perform everything in R. Note that all the datasets here may be downloaded using the link in the description box below.
In example number 1, wherein this was about the employees with the Medicare insurance and a regular insurance. Now suppose we don't have the R data regarding this, what we may do is to input everything manually. So we input 3057445 or simply these values, which refers to Medicare. And then similarly, we have 104121, which are the values in the object named regular. We may verify if we're able to put the correct values in Medicare and regular. Then eventually, we may try to compute for the mean of Medicare and mean of regular. We may also compute for the variance for the Medicare and the variance for regular. And lastly, the length or the sample size for the regular and the Medicare, which are supposed to be 7 and 6. Now for us to perform R, what we must do is actually to assign another object, let's call it as visits, and then simply write all the values here in one object. So we have 3057445, which refers to the number of visits of those with Medicare, and 104121, which refers to the number of visits of those employees with the regular insurance. And then we're going to have another column, which is let's call it as plan. 1 here refers that the plan is Medicare, and 0 means the plan is the regular plan or the regular insurance program. And then what we may do is to combine those two objects by using what we call the cbind function. So let's call the data as Medicare, then arrow, then cbind, and then visits, comma, plan. So this indicates that these two columns or these two objects will be combined to a single object with the name Medicare. You may take a look at the dataset and you will notice that it now has two objects, visits and plan. And then further, we convert it to what we call a data frame so that it's considered as a data set. And then we have to assign 1 as Medicare and 0 as regular. That is why we have Medicare $ plan, arrow, then factor, Medicare $ plan, and then labels equals C, regular, and then Medicare. So note that regular comes in first since that is 0 and Medicare comes the second since that is 1. Again, the one with the lower code is the one that comes in first in the labels option. Then after that, we may type Medicare to see what happens, and then we may compute for the mean of the two groups to check whether we arrive with the same answer. So that should be 4.0 and 1.5. We may also take a look at the variance, which is supposed to be 4.67 and 1.9. And lastly, for the length or the sample size, which is supposed to be 7 and 6. So once it's verified, we may perform the t-test for two means using t.test, then the variable in which the means were computed from, in that case visits, and then the grouping variable, so that is plan. So we have two groups of plan, the Medicare and the regular. The object name, which is Medicare, which is this one, and then var that equals true, since we assumed here that the population variances are equal. However, if there's a raw data, just open it. So you may open Medicare.rdata and then simply type t.test and then visits tilde, then program, comma, and then Medicare, comma, and then var.equal equals true. And we're going to have the same output. So notice here that the t-statistic is the same as the one that we computed. Likewise, the degrees of freedom is 11. And the p-value is 0.03319. And what we got is 0.0332. So since the p-value is less than 0.05, then we reject the null hypothesis and conclude that there's sufficient evidence that then the alternative hypothesis, the mean number of visits to a doctor of all employees with Medicare is not equal to the mean number of visits to a doctor of employees with regular insurance program. Okay, so as easy as that. Now on the sample write-up, we may further add what we call again the confidence interval. So employees with Medicare at an average visits their doctor more than 2.5 times. Now the value which is 2.5 times here is actually the difference between 4 and 1.5. And then the 95% confidence interval is 0.2 to 4.8. So we have here the sample mean difference, x bar 1 minus x bar 2. So that's 4 again minus 1.5. And it's 95% confidence interval. Okay? So the question is, how do we compute for the 95% confidence interval? How did we come up with this? Or how did R compute for these values? So again, this is the 95% confidence interval for the difference mu1 minus mu sub 2. So note that we computed t in this form. And what we're interested here is the mu1 minus mu sub 2. So if this is what we're after here, we simply have to cross multiply this standard error. So that's t times this square root here. So that will be t times some square root here is equal to x bar 1 minus x bar sub 2 minus mu sub 1 minus mu sub 2. And if we're interested in this value, we may just transpose this one, and this one we may transpose on the other side. So that gives us mu sub 1 minus mu sub 2 is equal to x bar sub 1 minus x bar sub 2. And then this value of t. So plus, as we know, that's plus and minus since t is positive and negative for two-tailed tests. t and then some square root here, which is the standard error of the differences. So that gives this formula. And substituting similarly, x sub 1, x sub 2, n sub 1, s sub 1, n sub 2, and s sub 2, using these values, and with t as the critical values of t, by simply getting qt 0.025 and qt 0.975, and then the degrees of freedom, which is 11, we're going to make use of t as 2.2010. And then again, these are the sample mean 1, sample mean 2, and other values which are s sub 1 squared, s sub 2 squared, n sub 1, and n sub 2. And what we're going to have is 0.24 up to 4.76, which is exactly the same as the values generated by R. Now note here that since our null hypothesis implies that mu1 is equal to mu2 or the difference is 0, our alternative hypothesis implies that min sub 1 is not equal to mu sub 2. Note that since the null hypothesis implies that mu sub 1 minus mu sub 2 is 0, and this 95% confidence interval does not include 0, then that is why the null hypothesis was rejected. So that is why our claim was in favor of the alternative hypothesis. In item number 2, wherein our null hypothesis was that the mean asthmatic index of all patients treated with the drug is equal to those treated with the placebo, and that the alternative hypothesis is that the mean asthmatic index of all patients treated with the drug is less than those treated with placebo. Since there was no statement here about the population variances, that's why we made use first of a preliminary test which is called as the F-test for two variances, wherein the null hypothesis is that the population variance of the asthmatic index of the two groups of patients are equal, and that the alternative hypothesis is that the population variances of the two groups of patients are not equal. And so we computed for the test statistic F, which happens to be either 4.3204 or F equals 0.2315, in which DF1 and DF2 are both equal to 5. And then we also computed for the critical value, which happens to be 7.146 and 0.140. And since the test statistic is not in the area of rejection, that's why we did not reject the null hypothesis and concluded that there is no sufficient evidence that the population variances are not equal. Thus, we assumed that the population variances are equal and eventually used the student's t-test. Now, to do the F-test in R, as you open the file, notice that there are two essential columns which contains all the asthmatic indices, and the treatment column, which identifies whether a particular patient received the drug or the placebo. So in performing the F-test, we're just going to make use of the var.test function, followed by the column, which has the numerical values, tilde, and then the column that separates the data into two groups, in which that is treatment, and of course the file name, which is asthma drug. And we're going to have this output, in which, as you can see, the test statistic F, or simply the calculated ratio of the two sample variances, which is 4.3204, with DF1 of 5 and DF2, which is also 5. And we have the same p-value, which is 0.1342. That's why we did not reject the null hypothesis, since again the p-value is greater than 0.05. Now, as for the 95% confidence interval for the ratio of the two population variances, so again, this is the 95% confidence interval for the ratio of the two variances. Notice that the equation for calculating the value of the F statistic is in this form. And since what we're calculating here is the 95% confidence interval for sigma squared sub 1 over sigma squared sub 2, then this fraction may be expressed as s squared sub 1 times 1 over sigma squared sub 1. And similarly, this fraction may be expressed as s squared sub 2 times 1 over sigma squared sub 2. which is the same as s squared sub 1 over s squared sub 2, then this one will be expressed as sigma squared sub 2 over sigma squared sub 1. Thus, our f statistic is s squared sub 1 over s squared sub 2 times sigma squared sub 2 over sigma squared sub 1. And since what we're trying to find is the ratio of the two population variances, then sigma squared sub 2 over sigma squared sub 1 is f divided by s squared sub 1 over s squared sub 2. Or in other words, sigma squared sub 2 over sigma squared sub 1 is f times s squared sub 2 divided by s squared sub 1. Now for this value of f, remember that if we have the f distribution and this is 1, we have two critical values, the one on the left and the one on the right. And surely this value is less than 1 and this value is greater than 1. Now if we're going to use these values as the values of f here, using this f, we're going to have f with cumulative probability of 0.025, since again the area to the extreme of this is 0.025, times s squared sub 2 over s squared sub 1. And we're going to have f with 0.975 cumulative probability, which happens to be this value of f since this is 0.025. So the cumulative probability is of course 0.975. And multiplying that to s squared sub 2 over s squared sub 1, we are sure that this will be less than this. And somewhere between will be sigma squared sub 2 over sigma squared sub 1. So this is the 95% confidence interval for the ratio of the two population variances. However, what you must notice is that this is not the value that we are actually looking for. We're actually looking for sigma squared sub 1 divided by sigma squared sub 2, which is the reciprocal of this. So if we're going to get sigma squared sub 1 over sigma squared sub 2, we have to get the reciprocal of this part and also this part. So that will be 1 over f with cumulative probability of 0.025, s squared sub 1 over s squared sub 2, then 1 over the f with cumulative probability of 0.975 times s squared sub 1 divided by s squared sub 2. Now since we get the reciprocal of this side, this one, and this one, remember in algebra, if you have 1 less than 2 less than 3, and we get the reciprocal of these three values, so that is 1, 1/2, and 1/3, this will now be greater than as well as this one. Thus, we have to reverse the inequality, so this will be greater than. Now, in f distribution, if you have df1 and df2, what you must notice is that the reciprocal of the f with cumulative probability of 0.025 is just the f with cumulative probability of 0.975. That is why in the previous examples, the reciprocal of 0.140 is 7.146. And similarly, 0.456 is the reciprocal of 2.194. Thus, the reciprocal of f with cumulative probability of 0.025 is actually the f with cumulative probability of 0.975. And similarly, the reciprocal of f with cumulative probability of 0.975 is actually the f with cumulative probability of 0.025. Thus, we're going to have this one. And just for convenience, we may reverse these inequalities by transferring this on the left side and this one on the right side. So we're going to have f with cumulative probability of 0.025 s1 squared over s2 squared, and f with cumulative probability of 0.975 s1 squared over s2 squared as the confidence interval for sigma 1 squared over sigma sub 2 squared. In other words, we just have to multiply the ratio that we computed using the sample variances with these two values of f, which are just simply the critical values of the f test. So applying that concept in example number 2, suppose our s sub 1 is 8.1833 and our S sub 2 is 3.9370, then we're going to have this equation in which 0.140 and 7.146 are just actually the critical values of f that is generated using the R or the table. Thus, this value will just be 0.605 and this value will just be 30.874, which is the same as this confidence interval given by R. So again, what R did is simply multiply the calculated f or the ratio of two variances with the two critical values of f. So 4.32 were just multiplied with 0.14 and 7.146 to get 0.61 and 30.87. So similarly, if you made use of this as S sub 1 and you made use of this as S sub 2, then substituting these values as your S sub 1 and S sub 2, we're going to have 0.032 as 0.140, again, which is the critical value of f on the left side, and 7.146, which is the critical value on the right tail, multiplied to the ratio of these two variances. So this will be the output of R, which you notice is the same as 0.03 and 1.65. So note that this value of f was just computed if this is group 1 and this is group 2. However, on the original data, this is actually group 1 because drug is coded as 1 and placebo is coded as 2. If it happens that the code used for placebo is 1 and drug is 2, then this will be the result of R. However, what you must notice is that no matter how you compute the value of f, either this one on the numerator, this one in the denominator, or the other way around, wherein this one is the numerator and this one is the denominator, you're going to get the same p-value, which is 0.1342. And although they have a different 95% confidence interval, what you must notice is that actually the reciprocal of this one, 0.604, is actually 1.65. And the reciprocal of 30.875 is actually 0.03. And although they have different 95% confidence interval, what you must notice is that both 95% confidence interval includes 1.00, in which since the null hypothesis implies that the population variances are equal, or in other words, when you divide the two population variances, this is 1. And since 1 is included in the 95% confidence interval, then it supports the null hypothesis. That's why the p-value is greater than 0.05. Now to perform the student's t-test, all you have to do is to type t.test and then the same format, asthmatic index, tilde, then treatment, then asthma drug, then var.equal true because we assume equal variances. Now if the option here is true, then that tells R that the output must be the student's t-test. And this is the student's t-test. So we have the same t-statistic, negative 1.7982. The p-value may differ. It is because, again, this p-value is for two-tailed test. And since this is a one-tailed test, we just simply have to divide the two-tailed p-value by 2 to get the p-value of the one-tailed test. And dividing 0.1023 by 2, we're going to have 0.0511. Which still is greater than 0.05, so we're not going to reject the null hypothesis. That's why we did not reject the null hypothesis and concluded that there's no sufficient evidence to support the alternative hypothesis. As for example number 3, wherein our null hypothesis was that the mean platelet count of all patients diagnosed with dengue fever is equal to those diagnosed with chikungunya fever. And our alternative hypothesis was that the mean platelet count of all patients diagnosed with dengue fever differ with those diagnosed with chikungunya fever. And since there was no statement whether we may assume that the population variances are equal or not, we made use of a separate test, which is the F test for two variances. in which the null hypothesis implies that the population variance of the platelet count of patients diagnosed with dengue and chikungunya are equal, and that the alternative hypothesis is that the population variances of the patients diagnosed with dengue and those diagnosed with chikungunya are not equal. And as for the test statistic, we computed for the value of f, which are 22.968 and 0.044, with df1 and df2 of 26. Then we also found the critical values, which are 2.194 and 0.456. And since the test statistic is in the area of rejection, then we rejected the null hypothesis and concluded that there is sufficient evidence to conclude that the population variances are not equal. That's why we made use eventually of the Welch t-test. We also calculated the p-value, which is very, very small, which happens to be less than 0.001. Now, as you open dengue point R data, there will be two essential columns, which are the platelet, which contains the actual platelet counts of the 54 patients, and the fever, which indicates that particular patient either had dengue or chikungunya. So to perform the f-test, we just have to make use of the var.test function, followed by the column with the actual values of the platelet counts, tilde, and then the grouping variable, which in this case is fever, and then of course the file name, which is dengue. And R will generate this result in which the F statistic or the ratio of the two sample variances is 22.97 with df1 of 26 and df2 of 26. Now for the p-value, it's less than 0.001. And as for the 95% confidence interval, remember that this was computed by simply multiplying this with the two values of F. One F with cumulative probability of 0.025 and another F with cumulative probability of 0.975. And those F values are actually 0.456 and 2.194, which was generated using these two outputs in R. So this is the one with cumulative probability of 0.025 and this is the one with cumulative probability of 0.975. And we get 10.47 to 50.39. So this is the case when chikungunya is treated as group 1 and dengue as group 2. Now if it's the other way around, when dengue is considered as group 1 and chikungunya is treated as group 2, so substituting 16.0489 as your S sub 1 and 76.9148 as your S sub 2, then we're going to have a 95% confidence interval of 0.02 to 0.10, which again is just computed using the ratio of S1 squared divided by S2 squared times the two critical values of F, which are 0.456 and 2.194. So that gives us 0.02 up to 0.10 as the 95% confidence interval for sigma squared sub 1 over sigma squared sub 2. And what you must notice is that 22.97 is just the reciprocal of 0.04. 10.47 is the reciprocal of 0.0955. And 50.40 is the reciprocal of 0.0198. So no matter how you compute the 95% confidence interval, either this is group 1 or this is group 2 or the other way around in which this is group 1 or group 2, you'll have a 95% confidence interval which does not include 1.0. So since our null hypothesis implies that the population variances are equal, then dividing the two population variances will have a ratio of 1. And since both 95% confidence interval, as you notice, does not include 1, then the null hypothesis was rejected. And of course, that is supported by the p-value, which is less than 0.05, which indicates that we have no reason to doubt the alternative hypothesis. Now, in performing the Welch t-test, all you have to do is to replace var.test with t.test. So that's t.test and then still platelet, tilde, fever, comma, dengue, comma, and then var.equal equals false. So this false option here indicates that R has to compute or has to perform the Welch t-test. So given this output of R, which is again the Welch 2-sample t-test, it has the same t-statistic. Do not just be bothered with the sign if this is positive and the computed value we had was negative. Again, it is because group 1 and group 2 may be interchangeable. Next, for the degrees of freedom, we have 28.259 and the p-value, which is very, very small. That's why we rejected the null hypothesis and concluded in favor of the alternative hypothesis, that the mean platelet count of all patients diagnosed with dengue differ with those with chikungunya fever. Now, on how this 95% confidence interval for mu1 minus mu2 was computed, remember that we computed the t-statistic in this form since the population variances are not equal. Now, if you're interested with this value, all you have to do again is to cross-multiply this. So that's t square root of s1 squared over n1 plus s2 squared over n2 is equal to x bar sub 1 minus x bar sub 2 minus mu1 minus mu2. So if your interest is on this part, we may transfer this to the other side and this one on the other side. So mu1 minus mu2 will just be x bar sub 1 minus x bar sub 2. And then since t is positive negative, so I may write plus minus and then t. And then that square root s1 squared over n1 plus s2 squared over n2. In which that value of t may be computed using r as qt of 0.025 and qt of 0.975. And then the degrees of freedom, in this case, we have 28.259. And using that value of t together with x bar sub 1, let's say is 271.7407, s sub 1, which is 76.9148, n sub 1, which is 27, x bar sub 2, let's say is 55.1852, s sub 2, which is 16.0489, and n sub 2, which is 27, we're going to have these values, which leads to 185.59 to 247.52. Now again, since our null hypothesis implies that the mean difference is 0, or in other words, the mean are equal, and since this 95% confidence interval does not include 0, then that's why our null hypothesis was rejected. So that's why our claim was in favor of the alternative hypothesis, mu1 is not equal to mu2. Before we proceed with example number 4, let me just have a recap of what happened in items number 2 and 3, in which upon performing the f-test for two variances, the p-value in item number 2 is greater than 0.05. Which indicates that there is no sufficient evidence to claim that the population variances are unequal. That's why eventually we made use of the student's t-test. That's why in the var.equal, this is true. Thus, we're going to make use of var equal equals true whenever that the p-value in the f-test for two variances is greater than 0.05. And on the other hand, in item number 3, upon performing the f-test for two variances, since the p-value is less than 0.05, this shows that we have sufficient evidence to claim that the population variances are unequal. Thus, we made use of the Welch t-test. And that is the reason why var.equal here is equal to false. So in other words, if the p-value is less than 0.05 in the f-test for two variances, that is the time that we have to make use of false in the var.equal. Now moving on, example number 4, we will not perform that in R anymore since that is a z-test involving two means which is not available in R. We may already move on with the last one, which is about the increase in the CD4 count of stage 4 HIV patients who underwent the ART or the antiretroviral therapy. So we had this null hypothesis and alternative hypothesis. We had this t-statistic and the critical value, and we rejected the null hypothesis and found as well that the p-value is less than 0.001. Now, to perform this paired t-test in R, we may open the file And we will see that there are two columns, which is baseline and monitoring, which is the CD4 count 6 months after taking the antiretroviral therapy. So for us to perform, we just simply have to type t.test and then HIV-CD4 $baseline, comma HIV-CD4 $monitoring, and then paired equals true, indicating that we are performing a paired t-test here. And the result will be this one, in which the t-statistics is 6.2175, which is the same as this. Again, do not be bothered with the sign if that's positive or negative. Then df equals 8, and the p-value, which is less than 0.001. So this indicates that the null hypothesis was rejected and claimed that we have sufficient evidence to support the alternative hypothesis. Now we may write as well the sample right up in this form. It was evident that the mean CD4 count of all stage 4 HIV patients increased 6 months after ART. Their CD4 count increased by 121.2, which happened to be the X bar. Okay? So this is your X bar sub D. And this one, 76.3 to 166.2, or this one is simply the 95% confidence interval for mu sub D, which may be computed using the formula. So if we are interested on this value, we may just cross-multiply T with standard deviation of differences over square root of n, and that's X bar sub D minus mu sub D. And to get this one, we may just transfer this to the other side and this one on the other side. So that's mu sub D is equal to X bar sub D plus and minus T, then standard deviation of the differences over square root of n, in which this T may be computed using QT of 0.025 and 0.975, then the degrees of freedom, which is 8, and substituting X bar sub D as 121.2222, S sub D, which is 58.49.098, and N, which is 9. So we're going to have mu sub D, which is 76.26 to 166.18. Now again, since our null hypothesis implies that the mean difference is equal to 0, and since the 95% confidence interval does not include 0, then that's why the null hypothesis was rejected. And that's why we claim in favor of the alternative hypothesis.
Now, to understand the paired t-test, what you must notice is that the paired t-test formula is somehow identical to the previous formula, which is the t-test for single mean, or also known as the one-sample t-test. The only difference is that the formula for the paired t-test have subscript D, which stands for the difference. Now, if these two are identical, then we may say that we may use the t-test for single mean, or also known as the one-sample t-test, when working with two dependent means. It's just instead of working with the actual sample mean and the actual standard deviation, we're going to make use of the mean of the differences and the standard deviation of the differences. Let's take a look at this.
So in the HIV-CD4 data, as we type HIV-CD4, we will only see two essential columns, the baseline and monitoring. Now, suppose that we add another column which is increase using this code. So HIV-CD4 $increase, arrow, HIV-CD4 $monitoring, minus HIV-CD4 $baseline. So this indicates that there will be another column which is increase, which is simply the difference of monitoring minus the baseline. So after typing that, you may type HIV-CD4 and you'll notice additional column has been added, which is increase. Now, we may perform the t-test for single mean, which is t.test, and then this variable, HIV-CD4 $increase, and then mu equals 0. So this indicates that we have null hypothesis in which the mean difference is 0. And doing that, we're going to have this result for the t-test for single mean. And this was our result a while ago in the paired t-test. So notice that the t-statistic is exactly the same. Do not be bothered by the sign. The p-value as well is exactly the same. As well as you can see the 95% confidence interval. So this shows that the paired t-test and the t-test for single mean are exactly the same. It is just the paired t-test, instead of actually using the two columns, what it does is just it computes for the difference and then perform a t-test for single mean using the differences.
So that is about the statistical inference involving two means. If you think you learned in this video, you may click like, you may also subscribe for more of my videos soon. Stay safe, guys!